Hello friends! In this video, we're going to talk about bit shifting, one of the simplest and most powerful operations in programming. The idea is exactly what it sounds like. You take the bits inside a number and you slide them to the left or you slide them to the right. That's it. But here's what's interesting. This tiny operation is how computers multiply and divide by powers of 2 without doing any actual math. It's faster than multiplication, faster than division, and it's used everywhere from graphics engines to file compression. Let me show you how it works.
All right, let me show you exactly what shifting means. Look at the top row. That's our starting number in binary, 0000, 1011. Now, when we shift left by 1, every single bit slides one position to the left. The bit on the far left edge falls off and disappears. And on the right side, where there's now an empty spot, a fresh 0 comes in to fill the gap. That's the whole mechanic. Bits move, the edge bit drops, and a 0 fills in behind. Think of it like a row of books on a shelf. Push them all one slot to the left, the book at the end falls off, and an empty slot opens up at the other end. Simple shift, nothing magical happening yet. But the magic shows up when we look at what this does to the actual value of the number.
Now look at this. The number we started with, 0000, 1011. That's 11 in decimal. After shifting left by one position, it becomes 0001, 0110, which is 22. We doubled the number just by moving bits. And this isn't a coincidence. It's how binary works. Each position in a binary number is worth twice as much as the position to its right. So when you shove every bit one slot to the left, every bit's value gets doubled, which means the whole number doubles. Shift left by 2, you multiply by 4. Shift left by 3, you multiply by 8. The pattern is simple. Shift left by n, multiply by 2 to the power of n. And here's the cool part. Your CPU does this in a single clock cycle. No multiplication circuit needed, no looping, just slide the bits. That's why game engines and graphics code love bit shifts. When you see code multiplying by powers of 2, it's often written as a shift instead, because it's just faster. Now let's flip the direction and see what happens when we shift the other way.
Right shift is the mirror image. Every bit slides one position to the right. The bit on the far right edge falls off, and a 0 comes in from the left to fill the gap. And just like left shift doubled our number, right shift cuts it in half. 22 becomes 11. Shift right by 2, you divide by 4. Shift right by 3, you divide by 8. Same pattern, opposite direction. But there's one detail worth noticing. When you shift right, whatever bit falls off the edge is gone forever. So if you take the number 5, which is 000000101, and you shift it right by 1, you get 00000010, which is 2. Not 2.5, just 2. The fractional part disappears with the bit that fell off. This is integer division. The same kind of division you get when you divide two whole numbers in C and the remainder gets thrown away. Bit shifting doesn't round, it doesn't keep decimals, it just drops what falls off the edge. Now, there's one more thing about right shift that trips people up, and it has to do with negative numbers. Let me show you.
Here's the part that catches people off guard. There are actually two kinds of right shift, and which one you get depends on whether your number is signed or unsigned. We covered signed numbers and the signed bit in the previous video on 2's complement, so I'll keep this quick. On the left, we have a logical shift. This is what happens with unsigned numbers, the kind that are always positive. Bits slide right and a 0 fills in from the left. Clean and simple. On the right, we have an arithmetic shift. This kicks in when you're working with signed numbers, the kind that can be negative. The leftmost bit, the sign bit, gets copied into the empty spot instead of a 0. So if your number is negative, that leading 1 keeps copying itself in, which keeps the number negative after the shift. If the sign bit had been a 0 would copy in. The reason this exists is so that dividing a negative number by 2 still gives you a negative result. If a 0 filled in instead, a negative number would suddenly flip to a huge positive value, which would break the math. So the rule is simple. Your compiler picks the right kind of shift automatically based on the type of your variable. You don't choose, the type chooses for you. Just know that both versions exist because when you read code that's bit shifting signed integers, this is what's happening underneath.
So where does this actually show up in real software? Everywhere, honestly. Top left, graphics and game engines use bit shifts to scale coordinates. When a game doubles a sprite's size or moves objects across a pixel grid, multiplying by powers of 2 with shifts is faster than calling a multiplication instruction. Top right, packing data. When you store a color in an image, the red, green, blue, and alpha channels each take 8 bits, and they get packed into a single 32-bit number using left shifts. The same Photoshop file you open on your laptop is full of pixel data packed exactly like this. Bottom left, flags and permissions. When a system stores 8 different yes or no settings, each one gets its own bit inside a single byte. Shifts are used to flip individual bits on or off without disturbing the others. File permissions in Linux work this way. Bottom right, straight up faster math. Writing x times 8 and x shifted left by 3 give you the exact same result, but the shift version skips the multiplication unit entirely. Modern compilers are smart enough to do this optimization for you, but in performance-critical code, programmers still write shifts directly to make the intent obvious. Bit shifting isn't some weird academic trick. It's a tool that's quietly running underneath almost every app on your phone right now.
All right, let's wrap this up. Bit shift is just 2 operations. Left shift slides bits to the left and multiplies your number by powers of 2. Right shift slides bits to the right and divides by powers of 2. The CPU does it in a single instruction, which makes it faster than regular multiplication or division. That's why it shows up in graphics code, in data packing, in permission systems, and in any place where speed matters. The next time you see those double arrow symbols in code, you'll know exactly what's happening. Bits are just sliding left or right, and the value of the number is doubling or halving with them. If this video helped you understand bit shifting, hit that like button and subscribe to Webronaq for more clear, no-nonsense explanations of the concepts that actually matter in programming. I'll see you in the next one.